Hello and welcome to our lab on Kirchoff's laws. Now, a lot of times, as we saw in Ohm's law, we can have circuits that have components that are either in parallel or are in series. And sometimes we can have a complex circuit that we can reduce by combining resistors in parallel or series to a simpler circuit that we can do an analysis on. Now, in some cases, a series does not simply reduce to a series combination or a parallel combination. And one of our examples is a circuit that has two loops. And so on this piece of plywood here, we have that sort of circuit constructed. And so I've got an outer loop here, and then there's a bridge here in the middle. And the resistor has a bridge on it, but then there is a power supply here and there. And so you see that none of these resistors are in series with any other resistor. And in fact, none of those three resistors are in parallel with any other resistor because they don't share the same endpoints because of this power supply here. So I have three resistors, R1, R2, and R3. And I have two power supplies. I'll call this V1 and V2. And basically, to sort of attach this to something in real life, I've got my power supply here, and I'm going to energize this board. And so I've got a plus 12, a 12 volt range that I'll attach to this far left side. It has a positive sign underneath it. There is a common COM, which means ground, that I'll attach to the middle here. It says negative, but this is really ground here in the center. And then I have negative 5 volts coming from this quad power supply that I attach over here on the far side where it has a double negative. So this is common, more negative, it's negative 5 volts, and then more positive, positive 12 volts. And I'm not using the variable part of this supply as I may have done in Ohm's law because I don't want the voltages to vary. I just want a constant voltage, so I'm using the quad part over here. 12, negative 5, and common going to my board. Now, behind the board, if you take a look, these wires are attached up here so that this voltage source here represents the 12 volts, right to left, and this voltage source here represents our negative 5 volts, right to left. And then here I've got attached my resistors. Then up here at this junction area, I've got a place where I can read currents. I can put an ammeter here to read the current in this branch. I can put an ammeter here, we'll call that I1. We'll put an ammeter here to read the current in this branch, we'll call that I2. And then I can put an ammeter here to read the current in this the rightmost branch, we'll call that I3. So we have, again, V1 and V2, R1, R2, and R3, and I can read the currents, I1, I2, and I3. So I've sort of defined and labeled my voltages, resistances, and currents. Now when we perform this lab, we're going to actually measure the values of these resistors and the values of those three voltages. And so first of all, before I turn on this power supply, I want to measure my resistances. When you measure resistance that's in a circuit, you have to turn off the power and you have to disconnect the resistor. I can do that by pushing down on this tab and pulling the resistor out. I can take the resistor completely out. And now I have this resistive component here. I'll take my ammeter, or my voltmeter, and I'll turn it around to the ohm setting, and then with the red lead in the volt ohm range, the black lead in the common, now I would take these probes and I'll read the resistance. So, reading the resistance, I just grab it just like that. I can put my thumb strongly across it. Now you think, oh, when you do that, Dr. Kottman, you are putting that resistor in parallel with yourself. That's true, but I'm a very large resistor, and so it's still going to read a pretty true resistance. You can bypass that, but you can't get as good a grip on it. So I'm going to read this resistor. So I'm measuring across it 1,993 ohms. 1,993 ohms. I want to hold the resistor with one hand and the probe, and then attach it to the other right here. So I've read my resistance. Now I can put it back into the circuit and read the other two resistors, but I'll let you do that. And your resistors will have different values from my resistors. They're not the same. All right, so now I've read out and I've measured the three resistances. So I know R1, R2, and R3. Those are all known values. Now next, I want to measure my voltages. So I turn the power supply on, and I take this meter and I dial it around to DC volts. It's the V with the dashed line and solid line, not the wavy line, not the sine wave line. All right, so now this probe is going to read volts. And so I can take it here and I can put it across these two lower tabs. All right, let me turn on my power supply. Put it across these two lower tabs. And I'm reading 11.99 volts DC, which is actually a lot closer than I thought it would be. I want to write down the exact values of voltages that I read, along with the corresponding uncertainty. So my uncertainty here, this is a digital device, and it's reading 11.99. Well, my uncertainty will just have to be the least count here, which would be 0.01 volts. So that's the resolution of the instrument. That's just what I'll use. There may be some documentation on this that could give me a more accurate value of the uncertainty, but for now I'm just going to assume that it's the value of the least count. So 0.01 volts, plus or minus, it will be my uncertainty here. All right, so I do that with both, and I get a voltage measurement. And be sure that you're consistent with your leads, because you turn these around, you'll get a negative instead of a positive, or a positive instead of a negative. So let's read our voltages right to left like this. Now, once you've got your voltages, V1 and V2, then that's two more unknowns that are taken care of. The third unknown is the values of those currents. And let's not read the currents yet. All right, we'll come back and test those currents in just a few minutes. But for right now, let's talk about how to use what we do know, the resistance of all three resistors and the voltage of those two power supply voltages, and use that to solve for and to predict what these currents, I1, I2, and I3, are in each of those branches. Okay, so I've drawn a schematic representation of our circuit board up here on the chalkboard. And so you see you have V1, this is our 12 volts. It's a known value, or close to 12 volts. Don't assume, you have to measure. We also have V2, this would be the negative 5 volts from here to here. And then, or let's talk about it this way, because this is common and this is negative 5, you're going from a lower to a higher, so that's why I've drawn the long line here, short line there. The short line indicates that this side is more negative. And so as I look at that, I'm going to say, okay, this is the negative side, this is the positive side of that power supply. So here's my negative 5 volt supply, but because this is common, our voltage is rising from right to left, from negative 5 to 0. Now over here, this is the more negative side. This is close to the common portion here, which is ground. I put a little ground sign. And then from here to there, I've got an increase in voltage by 12 volts, right to left. And so there's an increase up at the negative here, positive there. I'll draw my long side here, short side there. And so I've sort of indicated the polarity of these power supplies. Now, my resistors here, before I can sort of indicate a polarity for the resistors, I need to make a guess on which direction the current's going. And so it doesn't even have to be a good guess. Let's do it like this. You see I've drawn in these three positions where we're going to measure current in a few minutes? So let's talk about the current here. I'm going to use orange chalk to indicate that these are unknown values. So I've got a current flowing this way. We'll call it I1. Let's say I've got a current flowing up this direction through the center branch. I'm going to call it I2. And then let's say I've got a current going to the right here, I3. And so this current I1 is the same current that flows through here and around. This current I2 goes up through there, and the current I3 goes here and around. So three really branches here from, let's choose this node up here. From this node, you see you have three branches, 1, 2, and 3, and those are the three currents associated with each of the branches. And so now that I've chosen a direction of current, let me sort of choose the polarity of my resistors. And again, really this is unknown because I haven't proven this, but because I've chosen the current to go at I1 to be a clockwise current, that means that as we go into a component, we will give it a positive sign if the current arrow goes up into it, and a negative sign where the current arrow exits. So current goes from positive to negative, conventional current. Now over here, I2, we've chosen this to go up through this resistor. So we'll let this be the positive side and this be the negative side of that resistor. Current flows up through it. So the direction of I2 determines how we label the polarity of the resistor. And then current I3 goes clockwise here. And so the arrow will go down through resistor 3. So we'll make the entrance of the current I3 arrow causes that resistor 3 to be positive up here and negative down here. So we've sort of chosen these seemingly arbitrary polarities of our resistors, but that's going to allow us to set up our equations. Now if we've chosen the wrong current, once we solve this, we're going to get a negative value for that current. If we get a negative value, it shows that we've assumed the wrong direction, and then we have to go back into our drawing and reverse that in order to make our currents, all currents, positive. Positive meaning we've chosen the correct direction of the arrow. So if we get a negative current, no worries. It just means that we have drawn our arrow the wrong direction in real life. Alright, so let's make some equations now. And the way we make the equations is this. We use Kirchoff's rules. Kirchoff says that for any loop, all the voltages in the loop must add up to 0. This is Kirchoff's law for voltages. So let me look at this left-hand rectangle and ignore the rest of the circuit for now. And I'll say, okay, let me set up a clockwise loop. I could have chosen counterclockwise. It doesn't matter. And it doesn't matter where I begin my loop because everything sums to 0. So let's say I begin the loop right here, right where the ground point is. And let's go, we're going clockwise around the loop. And so as we go to the voltage supply, V1, we notice it goes from negative to positive. I have a voltage rise. That means I'm going to use a positive sign. So positive V1, that's our first thing. And now let's get over here to this current, to this R1. Now R1 is positive here, negative there. I chose it that way because of my current direction that I arbitrarily chose. And so this is a voltage drop from positive to negative. So I'm going to say minus. I could call this voltage here. I didn't measure this voltage, but I did measure the resistance. I know from Ohm's law that voltage is equal to resistance times current. So here my voltage across this resistor is R1, the value of the resistor, times I1, the value of the current. So the voltage of this component is R1, I1. I use my minus sign because it's a voltage drop, I'm assuming. And so I'll say minus R1 times I1. And this I1, of course, is an unknown value, so I'm going to use orange for now. I1. Now, as we go around here, we have this component in our loop. So we've got a voltage supply, a resistor, whose voltage is R1, I1. This is where our meter is. Okay, here's another meter. Now we get to another resistor. So this is where voltage is dropped. Voltage doesn't really get dropped across the meters. They have really low resistances. All right, so R1, I2. And so we've chosen a clockwise current, a clockwise loop. So as we go down through here, we notice we come to the negative sign and the positive sign. So this is a voltage rise. So we'll say plus. And then the value of this voltage here is, according to Ohm's law, R2 times I2. So it's a plus R2, and then I'll use my orange chalk for my unknown here, times I2. So I've looked at all three of these components, a voltage supply and two resistors, and I've made an equation here, but Kirchoff's law for voltages says that all of these voltages, these three voltages, you sum them up, you have to get 0. So I'm going to say equal to 0. And there's my first loop. All right, let's take a look at this right-hand loop, and we'll do it the same way. So let me make again, a clockwise loop. And let's start, as we did before, to the right of our power supply. Just arbitrarily chosen starting point, arbitrarily chosen direction. I could have gone counterclockwise. But let's do it like this. So we'll start here. We have a voltage rise. So that's V2. So I'm going to say positive V2 minus the value of this voltage here, which is R2 times I2, the center branch. And so I'll say minus R2 times I2. And again, I'll use the orange here for my unknown I2. And then finally, as I go around the circuit, I get to I3, which is traveling through this resistor. And so it's positive to negative, another drop. So minus that voltage, which is R3 times I3. So I'll say minus R3 times I3. So I have all my components there, these three voltage components, V2, R2I2, R3I3, and they have to sum up to 0. So I'll say equals 0. Now, the issue is with our two loops, we have two equations, but three unknowns. You see, unknown is I1, I2, and I3. Those are all unknown values. And so we can't solve an equation or two equations with three unknowns. So we need a third equation. Now we could choose this outer loop, but that's a circular argument, and it's going to come back around to two equations and three unknowns. So what we really need to do is use Kirchoff's law for currents. And as it turns out, anytime you have a junction like this one, and three currents associated with it, I1, I2, and I3, or just any junction with any number of currents associated with it, the sum of the currents going into the junction and out of the junction has to equal to 0. And so doing that, I take a look here, the currents going into the junction are I1 and I2, and the currents leaving the junction is I3. And so with that in mind, let me make an equation over here. This is Kirchoff's law for current junctions. And this says that I1 is positive because it's entering the junction, okay, plus I2 because it's also entering the junction, minus I3 because it's leaving the junction, is equal to 0. And now with that said, I can look here and I can state one of my currents in terms of the other two. Let's do it for current 3 since it's the one leaving the junction. And so let me rewrite this. I1 plus I2 equals I3. So let me square off that equation. Now with this, I can make my substitution. So let me go over here, and this equation that has I3 in it, I'll substitute I1 and I2 for that. So let me rewrite this equation. So this will actually be V2 minus R2I2 minus R3I3, but instead of I3, I'm going to put in I1 plus I2. So in parentheses here, I1 plus I2 equals 0. And so now that I've made that substitution, I'm down to two equations. This one for the left-hand loop and this one for the right-hand loop that have two unknowns, I1 and I2. And now, using some algebra, it'll be easy for me to solve for I1 and I2, and then to go back and find I3. So I can solve for all three currents. And so if it turns out that one of my currents is negative, all that indicates is that I chose arbitrarily the wrong direction of the arrow, and I need to go back and flip it. And so then, now that we've predicted our three currents, let's go back to the circuit board and test to see if our predictions for those three currents was correct. So here I am back at the circuit board. Now, mathematically, I've gone through my two equations with two unknowns. I've solved for I1, I solved for I2, and then I took those two equations and I put them back into the Kirchoff's current rule for junctions and solved for I3. And so now I've predicted mathematically my three currents, and it's time to come back over here to the board and test them. Now remember, if I got a negative value for a current in my calculations, that means that I assumed the wrong direction for the arrow. And so, so let's just kind of take a look. I haven't actually gone through the calculations, but let's assume that I have. And I want to read the current. So the way I'll do that is, first of all, I'll take my ammeter, and I'll take this red lead out of the volt-ohm range and put it over here in the 300 milliamp range. Now it's going to read current. Be careful with this, because if at this point you were to put it across the power supply or one of the resistors, you would short across it and you would likely blow that fuse, and then you'll have to change the fuse. You have to take the back off, unscrew the case, take the case apart, pop out the bad fuse, put in a good fuse, put everything back together. It takes about 5 minutes. So be careful here. Now I'll dial this around to AC amps. It's the amps with the dotted dash line on it. And now up here are three opportunities to read current. So let's read I1. So I'll take this little orange jumper wire out of there. Now there's a break in the circuit, but I'll replace that jumper wire with this. Now I had estimated my current to go that way, and so positive to negative, I'll put my red lead right here, and I'll put my black lead right there, and I'm reading a current. In this case, this is 3.4 amps. And so what that tells me is that my direction that I chose for that is correct. And so when I solved for that current, I would have gotten a positive 3.4 amps. Now, I'll put this jumper back in, and at this point, I will measure these other currents. And in doing that, maybe I might measure in the direction of my arrow, my chosen arrow, a negative value. This would indicate, all right, that my original arrow that I chose was in the wrong direction. So by this, you can test all three currents. You're going to compare those to your calculated values using percent difference, a percent difference calculation, and hopefully the difference will be very, very small, since you're using very precise instruments and you did your calculations correctly. So have fun with this. It's tedious, a lot of math, but I think you're going to do very well.